Okay, so welcome everyone. This week was the last time when we didn't have an ITC colloquium because of the many talks that we had, but gladly next week we'll resume the ITC colloquium. So stay tuned for the announcements. And today we'll start with a talk by an Italian. You can tell that from the fact that Galileo is portrayed. He pioneered many of the methods that we currently use in astronomy. And looked through a telescope. That was amazing. And so Fabio Pacucci will tell us about the dialogue concerning two interpretations of the little red dots that were discovered by the Webb telescope, and we look forward to hearing that. And then we'll hear from another person from the CFA, Joseph Michael. Where is he? Over there, yes. He actually gave a talk at the Black Hole Initiative, and we asked him to elaborate on details that were not included, so we hope to hear that. And it's about Sagittarius A-star mid-infrared flares with the Webb telescope. Very much looking forward to that. And then Sebastian Monzon from Yale will talk about constraining the low mass end and the stellar to halo mass ratio with surveys of satellite galaxies. And finally, we'll hear from our own Razi Emami, who will tell us about probing black hole astrophysics using a novel correlation method. Fabio, take it away.
Can you hear me?
Yes.
All right. So hello everyone. Today I'm presenting a modern conversation on the nature of the little red dots, but from the perspective of a notorious work by Galileo. So in 1632, Galileo published a very famous book that was titled A Dialogue Concerning the Two Chief World Systems. And the entire pamphlet is basically a conversation between three characters: Salviati, Simplicio, and Sagredo. This was not a friendly conversation on earthly matters, but actually the stakes could not be higher. And Salviati was a supporter of the heliocentric system, Simplicio of the geocentric system, and Sagredo was a moderator and was summarizing what the others two were saying. So Salviati presented theoretical arguments and observations to dispute the geocentric system. And one of the most spectacular examples in the dialogue is about the phases of Venus. So in the geocentric system, if Venus is above the Sun, you will observe it always in full phase. If it's in between the Earth and the Sun, you will always observe it in crescent phase. So transition between full and crescent phase cannot be explained in the geocentric system. However, Galileo, a few years earlier, had observed with his telescope that Venus indeed transitioned from a full to a crescent phase, as shown in these original drawings. So 400 years later, regarding our problem, in this short talk I will show a couple of examples of how the high redshift community is using very similar arguments to understand the nature of the little red dots. So these are very compact and red high redshift sources. They were completely undetected before JWST. They are very common. They are typically 10 to 100 times more common than the faint end of the AGN luminosity function at the same redshift, and almost as common as high redshift galaxies. So what is the matter of contention here? We do not know what powers most of their light. So the only thing we know for sure is that they are compact, but then there are two extreme physical interpretations to explain what powers most of their light. Either they are AGN dominated or they are star formation dominated. In the first case, black holes seem to be overmassive and are also undetected in the X-rays. In the second case, the implied stellar densities are extreme. So in my last ITC Luncheon talk about 1 year ago, I presented the overmassive black hole paper. So today, I will introduce the other two. Today's version of the dialogue will be presented from my own perspective of a black hole guy, of course. So Salviati will be supporting the black hole hypothesis, while Simplicio the stellar one. But in this case, I have to warn you that we do not yet know what is the real answer here. So it may well be that Simplicio, after 400 years of being wrong, may turn out to be right now. And if you're asking at this point, where does this parallel with Galileo comes from? We actually performed a real dialogue written in Old English at a conference in Gargonza, which is actually very close to Florence, so very appropriate for the occasion, a few months ago. So this is where the whole Galileo thing came about. So the first problem for the black hole interpretation is the X-ray weakness, and most of the little red dots are undetected in the X-rays, even in very deep stacking analysis, so stacking different non-detections, basically. So Simplicial argument in this case would be, if they were standard AGN, they would be detected in the X-rays, right? But our response to this was, well, no problem, they could still be AGN, but they're abnormally faint in the X-rays. So we investigated this problem using GRR-MHD simulations of super Eddington accretion, and we found that the SCDs are intrinsically extremely X-ray weak, especially for mildly super Eddington accretion rates, so if the black hole is accreting just above Eddington, and if the black hole is not spinning, and if it's viewed at large inclination angles from the pole or the jet. So here I show our reference examples for super Eddington X-ray weak on the left and X-ray strong on the right, SCDs. The gray lines in both panels show the SCDs as seen from inclination angles between 10 degrees and 80 degrees, so from almost face on to almost edge on. And so the beaming effect is important in all cases. And as you can see, SCDs strong in X-rays have a harder spectra with a high energy bump, especially when viewed near the jet, while the X-ray weak SCDs completely lack these features. They are very soft and steep in the X-rays. At redshift 6, the X-ray weak spectra are completely invisible to Chandra, except if seen very close to the jet in a blazar-like configuration, while next-generation observatories, such as AXIS or LYNX, will be able to observe them from any inclination angle. So how steep are our SCDs? Here I show the distribution of the photon index, so the slope, basically, of the X-ray spectrum, for all our spectra. And the majority of SCDs has a gamma larger than 2, and actually the most common value found is an extremely steep gamma equal 4.4. Consider that standard AGN have typically 1.7, 1.8. So what is the physical difference between X-ray weak and X-ray strong SCDs? Typically, enhanced X-ray emission is linked to higher temperatures, especially at the base of the jet, as you can see here, and in the walls of the funnel. So higher temperature, much more X-ray emission. So what is the connection with the little red dots? This plot shows the 2 to 10 kV observed bolometric corrections. As a reminder, larger values of the bolometric correction indicate less X-ray emission. For 2 samples of little red dots, as you can see with yellow points here, and also the X-ray stack, so the most stringent X-ray limit. The bolometric correction from our SCDs are shown with blue points here, and as you can see, being above the observations, even the stacking, they can fully explain them. I'm also working with a graduate student, Pei Xin, with photonization models that take our super Eddington SCDs as inputs. So the question is, if such SCDs irradiate gas in the host galaxy, where would such a source fall on the BPT diagram? So this preliminary analysis shows that super Eddington X-ray weak SCDs are significantly shifted toward the linear regime compared to standard AGN SCDs. So we're now developing a new diagnostic diagram to select sources that are accreting at super Eddington rate, especially in the lower redshift universe. Coming to the second problem, the SCDs of these objects can be fitted by a large amount of stars, also fitted by a large amount of stars. So several papers investigated this issue, and for example, this paper by Josephine Baggen from Yale studied 3 spectroscopically selected little red dots at redshift higher than 7, and as you can see, the implied stellar surface densities are very large, larger than the maximum surface density typically found at the core of globular clusters. So in that paper, they suggest that such extreme stellar densities can lead to large velocity dispersions that actually in the order of thousands of kilometers per second that can mimic the broad lines that are used to infer the presence of the AGN. This idea was actually proposed by Avi a few weeks before this paper by Baggen. So in this case, implicit arguments would be, well, in the star-only interpretation, this leads to extreme stellar densities. They can mimic the broad line, so there is no need for an AGN, right? Well, our response to this is, well, with those stellar densities, you're going to collapse the stellar core and form a massive black hole anyway. So we are investigating this problem with three complementary approaches from a dynamical perspective. And first of all, how dense are typically the little red dots? With an undergraduate student here, we studied the largest sample of photometrically selected little red dots, about 500 of them from Cosmos Web and Primer. And in this plot, you can see the probability distribution function of the core density inferred at the center of these systems. And about 35% of them have implied stellar densities that are higher than the highest stellar densities measured at the core of globular clusters. So just to make you feel how dense they are, there is the same difference between the stellar density in the solar neighborhood and the highest stellar densities measured in the little red dots, as there is a difference between being alone in Phillips or having the entire population of China in Phillips. So with a direct n-body simulation of 1 million objects, we witnessed the formation, because of stellar collisions at the core, of a very massive star of above 10 to the 4 solar masses, slightly above 10 to the 4 solar masses in about 1 million years, so in a very short time. So in summary, these three complementary approaches lead to the formation of a very massive star between 10 to the 4 and 10 to the 5 solar masses. This very massive star will soon collapse in a black hole of a similar mass. So the punchline is that a black hole in the little red dots is pretty much inevitable. So how would Sagredo, the moderator, summarize this talk? Well, we do not know what powers the little red dots, but in the AGN interpretation, we may be witnessing widespread super-Eddington accretion for the first time, while in the stellar interpretation, we may be witnessing an unexplored route to form massive black holes in the early universe. Thank you.
Fabio, did anyone, given those stellar densities, did anyone calculate the TPE rate, the tidal disruption?
Yeah, this is actually a very interesting question. There is a very significant possibilities, especially if you form a very massive black hole at the center. You still have a very large density of stars, so there could be TDs, and we calculated with Suvijetari, actually the rate for TDE should be about 0.5 to 1 per year. And if you consider the plateau regime of a typical TDE, you could have a continuous emission basically coming from TDs. So it's very possible that also TDs don't emit in X-rays. Also, TDs are typically not observed for central black holes of above 10 to the 8 solar masses, and because it gets completely swallowed before getting tidally disrupted. So at least the measured black hole masses at the center of little red dots are lower than 10 to the 8. So it's a very, there is a paper actually on Archive about this kind of calculations as well. So it's a very interesting possibility. Yeah.
Okay, several things for the next version of, more extended version of your talk in the future. The local analogs of little red dots that we found, like around 2,000, 3,000 of them, they lie in the top left corner of the DPT, so they're out of the grid. Second.
So what are the are we talking about the green peas? Or
it's
what?
not green peas, it's these sources that were found by Zotov back in 2008, and there were like a few of them in SDSS, because SDSS was actually selecting against them. So the chance of getting their spectrum was low, because it was like weird quasar or something.
Okay.
Second, you have stellar densities like you mentioned, around 10 to the 6 or more per cubic parsec in the centers of globular clusters. And for some reasons, massive black holes do not form there.
Well, there is actually a paper suggesting that they can
In one,
form. Yeah.
yes. The stellar densities like this are in many. Like if you take any core collapse global cluster, you get the density like this. And also there's a question of whether these objects will ever core collapse because it's too big in terms of mass. And there's this two-body relaxation time scale and the dynamical segregation time scale. If you try to do the math, you'll see that they might not ever collapse. So the core collapse time will exceed Hubble times by orders of magnitude.
Well, in our calculation, actually they collapse in any case, even if you don't consider binaries, stars. So they're basically collapsing because the how do you say, it's the how can I explain, the orbit, say, take a couple of binaries, the orbital velocity, it's pretty low compared to what would be needed for the binaries not to collapse on themselves. So the collisional timescale is pretty low in our simulations.
Okay,
but
we can
yeah.
discuss this offline. And the third thing about X-ray, actually, in these local objects, those were the ones that, there was a paper called Do Some AGN Lac X-ray Emission.
Yeah.
And this was from 2015. And those are these sources. And one of them actually is detected in X-ray after 55 kiloseconds in Chandra with the, for a source at redshift 0.2, 0.17, there are like 7 photons.
Yeah.
And they're fully consistent with star formation if you assume that all H alpha that you see comes from star formation. So you don't need a black hole, that's the whole point. You might form the line by stellar winds, not a black hole.
You can form the line stellar winds, but it's also true that a few little dots are actually detected in the X-rays. So there is the sample by Kocheski, 341 from Cosmos Web and Primer, and they have a detection of 2 little red dots, X-rays, a few photons, as you were mentioning, and they are detected, and it's quite interesting to see. Say median redshift of this sample is like redshift 5 or 6. So this line here is the SCDs are seen from inclination angle from 10 degrees, okay? If you calculate what is the probability of seeing such a system within 10 degrees from the jet, it's about 0.6%, and then you have to multiply it because there are 2 jets, right? And this is approximately the probability, the frequencies probability of observing those 2 little red dots out of 341. So it's possible that we are just seeing the ones really in the jet. So I agree, a few little red dots are detected in the X-rays. There's a very minority of them though.
Okay, one last question, Tommy.
Well, I might be simplistical here, but as I recall, the center of the Milky Way has a cluster which is 10 to the 7 solar mass, 10 to the 7 stars in the inner parsec, as well as a million solar mass black hole. So, you know, what's the problem?
What do you mean?
Isn't that a compromised solution? It's both a cluster of stars, a dense cluster of stars, and a central AGN.
No, I don't see the problem in that case, meaning that in the Milky Way case there is a supermassive black hole there that already formed probably billions of years ago. In our case we are saying that the black hole is actually forming there because the stellar densities are very large. So we are actually in the process of seeing the formation of this thing. Formation time scale for such a black hole would be 1 million years to reach 10 to the 4 solar masses. Then, depending on how the accretion rate from stars onto the very massive star declines, then you have basically the collapse of this very massive star into a massive black hole because it basically leaves the Hayashi track when the accretion rate falls below a limit. So you are forming a black hole in a matter of a few million years. So I don't see the problem. In the Milky Way, there is already a supermassive black hole there. These may be systems that are actually actively forming massive black holes at their center. Yeah.
And of course, the main difference is the Milky Way is much bigger than the inner region, whereas in these galaxies, it's only that region which is making the system. Thank you so much.
Yep.
Oh, but right in the center of our segment, there's 10 million stars.
Can you all hear me? Okay, if not, I'll just scream. And that's not John. Okay, so I'm Joe McHale. I'm a NSF postdoc. I just got here in September, so if you haven't seen me, hello. Today I get to have the pleasure of talking about some of the first, that should say Sag star, that's behind Sag star, the first mid-infrared flares from JWST Mary, talking about the galactic center. So, this is one of my favorite images ever because I started with dust in undergrad, and this is just to go all the way from Milky Way scale galaxy, which is on the top. This is a Planck image of the 850 micron, 353 gigahertz, depending on what kind of notation you like, image of the dust in our galaxy. Those streamlines are showing magnetic fields being traced by the dust, and if we go deeper, or we go closer into the galactic center, we have the mini spiral where Sagittarius A star lives, where the cluster of stars we were just talking about lies, where all this gas and dust is magnetically held, not being allowed to collapse into Sag A star. And then, of course, we're at the CFA. I'm sure this is not the first time you've seen Sag A star in the past couple of years, the 4 million solar mass black hole that lies at our galactic center. Now, 4 million solar masses might sound like a lot, but if you measure the size or how much time it takes for light to go from one edge to the other, it's about 40 seconds. So Sagittarius A star really has a small dynamical time scale where things that happen in the accretion disk on one side, or one side of the accretion disk, they propagate very quickly into the other side of the accretion disk through turbulence very quickly, which you have turbulent motions, you create a lot of turbulent energy, and you can get flaring emission. Now, Sagittarius A star can only be seen at certain frequencies, certain wavelengths, because of all the gas and the dust. So we, unlike other little red dots and whatnot, we have to look through our galaxy. We have to look through 26,000 light years of gas and dust and stars, which block our view at certain wavelengths. So we're really only limited to see flaring emission from Sagittarius A star in the radio to submillimeter parts of the infrared and the X-ray. Everything in the optical is obscured. You have at least 30 magnitudes of obscuration between us and Sagittarius A star, meaning good luck. I mean, if we had a humongous flare, maybe, but that might blow the Milky Way apart. So who knows? The thing is that we need to stick with the infrared. Now, this has been seen before. Mid-infrared flares, or flares from Sagittarius A star, have been seen before at radio, submillimeter, X-ray, and near-infrared. So on the left here is the brightest flare from Sagittarius A star ever seen before. 1 count per second at the 2 to 8 keV range, which sounds like a lot. I'm not an X-ray astronomer. But that stationary point right there is a magnetar. In 2013, there's a galactic center magnetar that just happened to go into outburst and was one of the brightest X-ray sources. And then that blip that you see is Sagittarius A star producing its brightest X-ray flare ever. Now, to give you a sense of scale, this is about 20 minutes. So you have a very bright X-ray flare, about 20 minutes in duration. On the right side here is a near-infrared image of the galactic center with this little dot right here that goes in and fades out is Sagittarius A star during its brightest ever detected near-infrared flare. So this was actually caught kind of in the middle, so this flare might have been even brighter than we actually expected. And this has been seen with changes in 2019 that might suggest that in 2019 something happened with the accretion flow or the accretion rate onto Sagittarius A star, which suddenly made it a whole lot brighter. What's missing from this is the mid-infrared. And up until JWST launched, the mid-infrared was not well covered. We didn't have the spatial sensitivity, the spectral sensitivity, nor the photometric sensitivity or stability to actually measure Sagittarius A star's flux in the mid-infrared. So this is one of the best images of the mini spiral and Sagittarius A star at 8.6 microns before JWST launched. And you can see at the location of Sag A star, which is marked, there's nothing. To give you a sense, this observation had a 3 sigma upper limit of about 23 millijanskis for how bright Sagittarius A star or its flare was in the mid-infrared. But JWST did launch in 2022, and in 2024, April, just a couple months ago, we observed it with JWST, Sagittarius A star with JWST for the first time. And this doesn't want to play, but I'm going to make it. And we detected it. So on the top here is an inset image of Sagittarius A star in black as a function of time. And on the bottom are our light curves. What's special about JWST MIRI is that we have spectral coverage, multispectral coverage across a wide swath in the mid-infrared. So not only did we detect a single flare from Sagittarius A star, the first one, that lasts 60 minutes or so, but we detected it at 4 different bands, 4 different mid-infrared bands. And I could watch this all day, but maybe it's just because I've been trained to love Sagittarius A star. Let's give this thing one more time to play. What's special is that we see 3 peaks in the mid-infrared. It starts to brighten, and then 1, 2, 3, and fades away. Let this play for a couple more seconds. And this is special because this tells us something about what's the origin of this emission around Sag A star. Okay. Oh no, that's not what I wanted to do. Come on. And not only did we have JWST MIRI, but we also had other multi-wavelength partners. We had the Chandra, a new star that did not see an X-ray flare, which is important when we talk about the modeling. JWST, of course, and SMA, which is, of course, CFA's flagship sub-millimeter observatory. And while we didn't see any flare in the X-ray, we did see a peak in the sub-millimeter at 220 gigahertz, or something like 1.3-ish millimeters, again, depending on what you like, that was delayed by about 10 minutes relative to the last peak. I don't have time to get into that, unfortunately, today. But what I do have is, I'm a radio astronomer. I love spectral indices. So we have 4 mid-infrared bands. We can look at what the change in the spectral index is as a function of time. Now on the top, we've just normalized our light curves to take into account all different extinction effects and all that fun stuff that I don't have to think about as a radio astronomer, but I have to think about as a mid-infrared astronomer. So what we see is that at the beginning of this flare, near 10 to 20 minutes, the spectral index is flat. There's no change in the color of your flare. Then all of a sudden, around 30 minutes, you get this sudden decrease, this change of about a half, 0.4, around 30 minutes. And then again, it levels off, which is really indicative of the processes like synchrotron cooling, which is occurring in the hotspot itself, or this flare. So what we've done, or what we did, is we did an analytical model to look at what might cause this flare. So in my illustration, which looks like maybe a third grader did it, Sagittarius A star is at the center, and this fluffy accretion flow is around it. Now, we have this flare region, which, depending on who you talk to, what kind of GRMHD simulations you look at, it could be just a hole in your accretion flow, it could be an orbiting hotspot, it could be one that transitions to the other. But what's important is that this flare has a certain size, it has a magnetic field strength, and we're going to inject electrons analytically into it, have it orbit Sagittarius A star, and see what the light curves come out of it are. And this is the result, which is not too bad. So in the dots are the actual JWST light curve. The lines are our 4 wavelengths, and then just don't think about the other 2. We capture most of this variation in the light curves, where we see this initial achromatic rise in the flux, this plateau-ish region near 30 minutes, and when you look at the spectrum, the model spectrum, you see this sudden decrease in the spectral index, and then at the end, you get this tail off where the flare fizzles. Now, this is a very simplistic model, right? We're only injecting electrons. We're missing a lot of the physics that are behind it. However, we don't really need to, in future work that we're planning, we will add more things and look at GRMHD to compare the two. But in general, this works well. So this is just a beautiful image of the GRMHD simulations we will start to look at, where each of these little blobs is kind of, can produce one of these flares that we see in the mid-infrared. So we have 21 more hours to observe, or to analyze, which we're looking forward to. Thank you for listening.
So, Joey, I was not convinced that it's a flare in the sense that I haven't seen the quiescent phase and this jumping above it. In fact, you just calibrate the 2 endpoints at 0 and you claim it's a flare. But maybe the source is fluctuating. Like, how lucky are you that within the 1.5 hour you see a 1.5 hour flare?
So we did, we do have let's see, this is the 6th. So we do have a piece that came before it and after it. And this was the only one that showed something substantial.
Was it flat in those other?
It wasn't flat. You do see small variations, which we're not necessarily 100% convinced if they're intrinsic to Sagittarius star yet, or if they're just thermal noise of the detector or whatnot. But this kind of pattern has been seen before. And especially, going back to the multi-wavelength plot, the idea that we see SMA, which follows this 10-minute time delay that's been detected before, it comes just as the last peak has been seen. All these things kind of match and generally tell us that we believe that what we see has been seen before. So it's not out of the ordinary that all of a sudden we see this weird peak structure and nothing else with it.
It must be a high duty cycle because you were lucky to see it.
So if I remember my statistics correctly, you expect about 6-ish infrared flares, which typically near infrared beforehand, a day. So if you once every 4 hours or so, and I don't think we've done the statistics on this just yet, but 24 hour, you expect at least 6 or so flares from the roughly day of time that we've observed.
What instrument mode of Miri was being used?
MRS. So it's the only one that allows us to observe multiple frequencies at the same time. That's not 5 to 14 microns. We've seen Sagittarius star flare at 5 microns with Spitzer before, but everything above that has just been hidden behind the gas and the dust. So we wanted to get as much coverage as possible, especially for this spectrum. It's important for ongoing GRMHD work.
If you plot the SED of these 4 points, are they a power law? Are they curved? Or?
So we're having I shouldn't say an issue, because depending on who you talk to, dust is great. I at one point thought that. Because of all the extinction, right, we're doing everything in a relative sense. So we're taking some point in the light curve as our 0, effectively, and normalizing everything to 1 to take out all of our extinction. Which works when you're doing this kind of modeling, because when we're actually doing the modeling, we do the same thing. We don't care about the overall fluxes, we just normalize relative to the spectrum. In our modeling, we assumed an injection of power laws of P equals 2, which some people like, some people don't like. But we're actively working to get the extinction out and to maybe even subtract out all of the gas and the dust through SED fitting of the dust to hopefully extract
I
it.
was wondering if it needn't be synchrotron, but it could be thermal.
Your thermal typically stops around 300 gigahertz. So if you look at the overall spectrum of Sagittarius star, your sub-millimeter producing electrons are kind of a mix between thermal and non-thermal emission. It's certainly something we have to continue to look for, but I don't think at this point anything suggests thermal emission in the infrared. It certainly doesn't in the infrared, and definitely not the X-ray.
Please.
That was very nice, thanks. In case the electrons are accelerated current field, you were showing at the last video.
Yeah.
So did you or anybody else compare the recognition rate and the acceleration time scale with the synchrotron cooling time scale?
So we do need to take into account synchrotron cooling with this modeling because it's only about 5 minutes for the magnetic field we found, which is about 40-ish Gauss. But we're injecting the power law of electrons in kind of a Gaussian time. So we're including synchrotron cooling in our modeling, and that's where you see the change in your spectrum, where you're injecting less electrons, energy into the system, and you suddenly get the change in the spectral index.
So you don't really look at where the electrons come from.
No, so if you look at GRMHD, right, turbulent motions, you pinch magnetic fields, you produce, I can't think of the name.
So I mean, what
Yeah.
I was asking, so like, you could calculate the reflection rate.
You
that
could.
was a much
Yeah.
more easy.
You could.
Compared to
Yeah,
It's as complicated as the solar
yeah.
magnetosphere,
Or
which
more.
we don't fully understand. Thank you so much.
Thank you.
Oh, yeah. Does this work? Can you guys hear me all right? Yes. Great. Just gonna put this in here. Okay. Well, yes, thank you very much for having me. Rudy Montez invited me, and looks like he got out of his meeting just in time. My name is Sebastian Manzan. I'm a graduate student at Yale University. I work with Frank Vandenbosch and other students in his group. And today I'm going to be talking to you about a recent paper of mine titled Constraining the Stellar Halo Mass Relation with Surveys of Satellite Galaxies. So hopefully you all recognize this plot. This is the so-called stellar halo mass relation, which is kind of the 0th order way for us to understand the galaxy-halo connection, or what type of galaxies live in what type of halos. And ultimately, what we want to do with this galaxy-halo connection is link the observable universe to what actually governs the dynamics of the universe, which is the dark matter. And if we have a good handle on the galaxy-halo connection, we can, of course, study the physics of galaxy formation. We can infer cosmological parameters, and ultimately, if we're clever, probe the nature of dark matter. But if you zoom in on the stellar halo mass relation, below roughly 10 to the 11 or so in host halo mass, you can see that this kind of looks a little bit like a frayed rope. And that's just because basically all of these models are extrapolations at this regime. And that's simply because there is no analog of these massive redshift galaxy surveys like SDSS at this scale. And so the low mass end of the stellar halo mass relation is not well constrained. There are, of course, big important steps being made in the right direction. One of these is a survey called Satellites Around Galactic Analogs, or SAGA for short. Recently, SAGA just published their 3rd data release, which has 101 Milky Way analogs with roughly 400 satellites, or roughly 4 satellites per host. And what's great about SAGA is that it's a photometric plus spectroscopic survey, which means that they have really good membership probabilities for each of their satellites. And the whole point of the SAGA survey was it was designed to answer this question of, is the Milky Way typical? To kind of place the Milky Way in a cosmological context, right? And so this is a nice figure from their paper that shows different satellite galaxy population surveys, local group, local volume through the ELV survey, SDSS, and of course, SAGA here in the middle. So what can we do with this great data? Well, of course, SAGA doesn't actually give us any information on the halo masses. All they give us, for example, one of their main data products is the so-called satellite stellar mass function, or satellite luminosity function. For the purpose of this talk, I'll use luminosity and stellar mass interchangeably, which of course they're not. But and so yeah, you can see here that you can basically, per host, say how many satellites you have, and of course what stellar masses they are. But that doesn't really help us, right? This is the observable. What about the thing that actually governs the dynamics of the universe? Well, in the lambda CDN context, we have a very robust model that predicts, given a host halo mass, the type of dark matter substructure that you expect to see around that host halo. And this can be categorized in something called a subhalo mass function, where here the link is, of course, the stellar halo mass relation. Okay. So how do we get our subhalo mass functions? Well, instead of going to these super detailed, high-resolution, zoom-in, n-body cosmological simulations, which are very computationally expensive, we've opted to use a model called SatGen, which under the hood uses extended pressure sector theory to populate its merger trees. So this is kind of a little schematic of a merger tree. And then for every infalling subhalo, you can assign it a position and a velocity, basically an orbit. And then you can integrate that subhalo's orbit according to an analytic host potential, which of course, being a semi-analytic model, means that you have incredible freedom, not only in your host potential, but also in the merger tree resolution that you select and in the cosmology that you select. And so this is great for 2 reasons. The first is that it's not hampered in the same way that n-body simulations are by numerical artifacts. And the second reason is that it's incredibly computationally inexpensive, which means that we can properly sample this effect called halo-to-halo variance, which I'll talk about in a second, just from the fact that we can sample several different mass accretion histories for a given host, or several different merger histories for a given host. So here it is, that host-to-host variance, or halo-to-halo variance. In our paper, we talk about these 3 different samples, S0, S15, and S30, which are kind of motivated here based on the host halo mass. So again, SAGA is a Milky Way analog survey. And so if you can kind of bear with the simplest assumption, which is that they somehow perfectly only select 10 of the 12 hosts, that would be the S0 sample. Of course, they're based on luminosity criteria, so they can't do that. And so what we've done is we basically just widened that distribution slightly for the host halo mass. And on the top panel, what I'm showing here is the mass accretion histories for 1,000 different host halos, and the corresponding subhalo mass functions for each of these samples. And what I want you to take away from this is that as you go to more and more mass mixing in the host halo distribution, your subhalo mass function variance also grows. And that's just because more massive hosts not only have more substructure, but they also have more massive substructure. And so here you might be including a subhalo mass function from a 10 to the 13 host alongside a 10 to the 11 host. But in the S0 sample, you still get this variance just from the fact that there's more than one way to build a Milky Way. Okay, so we have our subhalo mass functions. We can now convert them to something that's actually observable. So what I've done here is I've parameterized the stellar halo mass relation very simply, just as a single power law with a slope and a scatter. You can forget about that other term. It's technical detail that you can see in the paper. But the idea is that now I can create these kind of mock SAGA-like surveys, and I want to describe them in some way. If you're an MCMC aficionado, you might know where I'm heading. But the idea is that if I can describe these surveys using some summary statistic, then I can compare and kind of play these parameter recovery tests. So the two statistics that we use are the distribution of the most massive satellite per host and the number of satellites per host. And if you go back to your satellite stellar mass function, basically what we're doing is we're anchoring it on the x-axis and the y-axis, and then also using the correlation between these two distributions. So panels D are the stellar mass of the most massive satellites. Panel E is the total number of satellites above some magnitude limit. Of course, SAGA has some magnitude limit. and then their correlation. And this correlation is important because, again, if we're including host halo mass mixing, you expect this correlation to basically be able to tease that out. More massive hosts have more substructure that is also more massive, and so the number of satellites will grow alongside the stellar mass of the most massive satellite. Okay, so I've given you now all the ingredients for our forward model. The first thing is we create a Sachin merger tree sample. We assume some stellar halo mass relation. We observe this mock survey using our 3 summary statistics. We can sample the parameter space with an MCMC and then compare our highest likelihood model to what we've actually assumed and see what we get out. Ultimately, the goal is to ask these 2 questions. What constraints of the stellar halo mass relation can we get from surveys like SAGA? And how does host-to-host variance impact these results? So I'm just going to talk about alpha and sigma, the slope and the scatter. These are simple parameter recovery tests that we've done. On the top, I'm going to be holding some parameter fixed. In this case, it's alpha. Or sorry, on the top, I'm going to be allowing some parameter to be free. On this case, it's alpha. On the bottom, it'll be fixed, which is sigma, the scatter. And then here you can see that I have 4 different permutations of the truth value that we've implemented. So a steeper slope to a shallower slope. And we're doing pretty good in the S0 and in the S15 and also in the S30, as you can see from this 1-to-1 line. Right? Of course, there's some uncertainty that we have a handle on from our posterior distribution, but by and large, the medians are right along that line. So this is kind of encouraging. Maybe we can learn a little bit about the slope. But if we play the exact same game and now allow sigma to be free and hold alpha fixed, so now we're fitting for the scatter. Here I've, again, done 4 different permutations from a deterministic stellar halo mass relation all the way to what some might consider to be kind of gargantuan amount of scatter. You can see that we're not doing so well. And we do not recover the scatter, which is not unexpected if you now include more and more host halo mass mixing. And so this is slightly the opposite of encouraging. And we thought a lot about this, right? So why can't we constrain sigma? Well, it turns out that the scatter in the stellar halo mass relation needs to be basically huge in order to impact our summary statistics. Here what I'm showing is the variance in our first statistic, the number of satellites, and the variance in the stellar mass of the most massive satellite. The colored bands are kind of the default value that you get just from differences in mass accretion histories and also from this effect of host halo mass mixing in S15 and S30. And the black dots are basically the reverse of that, so no variance from mass accretion histories, just kind of artificially introduced scatter from the stellar halo mass relation. You can see that you have to go to basically 1 dex before you start impacting these kind of default values, before you start overcoming the signal that is already there from the halo-to-halo variance. A kind of secondary effect, which was nicely shown by Garrison Kimmel et al. In 2017, is that the slope and the scatter are actually degenerate. And that's because of this effect called Eddington bias, where the steeply declining subhalo mass function basically means that there's a higher probability of downscattering, a higher probability of upscattering low mass systems than there is downscattering high mass systems. And so a shallower slope is consistent with larger scatter, and therefore there's some degeneracy in these 2 parameters. And in the paper, we talk about future surveys that might go deeper and include more hosts, and I can show you some backup slides that I have for that. And we also talk about not only learning about the stellar halo mass relation, but also trying to constrain the host halo mass distribution with our forward model. And in the last minute or so, I just briefly want to plug the next project that we're doing, which now is all about the disrupted satellites. So in the first part, I've only talked about the surviving satellites that you could actually observe in a SAGA-like survey. But of course, we know that the outer regions of the stellar halo in the Milky Way, for example, is dominated by disrupted satellites that have been accreted onto the Milky Way. And so with the same kind of ingredients in our forward model, we can ask interesting questions about the stellar halo. What fraction of the stellar halo is built up from accreted systems? How does halo-to-halo variance impact the stellar halo? And is there a correlation, for example, between accretion history and stellar halo mass? So with that, I'll just leave up my conclusion slides and just point out that you can read the full paper here. Thank you very much for your attention.
Thank you, Sebastian. Any questions, comments? Go ahead.
Very What? So you said that you populate a merger tree using extended Press-Schechter mass function.
Yes.
So suppose you know what Press-Schechter idea is. What does that mean?
Yeah, so let's go here. Extended pressure. So I'm by no means an expert, and the model was developed over several different grad students that have come before me, but not extended pressure theory, the Sachin model. The idea behind extended pressure theory is that you basically assume that the early universe, the matter density field is a Gaussian random field, and then you can use this excursion set formalism to build up mass trajectories by convolving this matter density field with a window function, which in SatGen is specifically this sharp k-space window function, which is a little bit technical, but the idea is that by using that specific window function, you can now assume that the trajectories are Markovian, which means that they're unrelated, and you can basically sample from the halo mass function that you get from that trajectory and count however many subhalos you want based on some target mass or some target redshift for the host. It's a little bit technical, but in particular, SatGen has been calibrated very extensively against dark matter only simulations, and that's exactly what I showed here, actually. Sorry, this figure here. So here, the model here is the SatGen model, and the black lines are an n-body cosmological simulation. So the idea is that they've been calibrated against each other so that you can reproduce what the state of the art is.
We need to move on.
Yes. Thank you.
It's very yellow-like paper.
Hi, do you hear me? Okay. Hi, everyone. It's a great pleasure and honor to speak today. Thank you so much for your participation. So today I'm going to talk about the new polarimetric analysis of sub-millimeter basically flare near the horizon episode of MAD7, and then what we actually get from using the new EB correlation phase. So this is in a collaboration with a lot of people here. That's my great pleasure. You see that almost like more than half of them are from here. I mean, you can be one of them. That's always a great pleasure. But also among them, this is a project scientist of the ESG. That is the great pleasure, Jeff Bauer. And I'm going to convince you why it can be a novel thing. So let me start with the good news. As of recently, 2024, basically the multi-frequency campaign that was simultaneously being done with the ESG in 2018, they announced by Agaba et al. That is also ESG in BARV, that there is a very nice, very high energy, basically gamma ray flare from MAD7 that was detected since 2010. And that was very spectacular. When I was first talking with Mr. Bembo here, the director of Veritas, he was very excited that since 2010, they haven't observed anything, actually. And that's basically during 36 hours of the observation, around 350 GeV, the Ferox got basically doubled. But the problem, and you see that Fermilab and Veritas, they had them, unfortunately, no flare in radio. And that was heartbreaking. So when I saw this, I started wondering, no, it should be something there. So there is no flare currently detected in sub-millimeter from MAD7, despite the fact that, I mean, we're very lucky that Joseph, very accidentally, he's also talking about the first are very good, they're very informative, as we know and as I will show you. But why we haven't observed anything yet for sub-millimeter? So here I'm going to actually tell you that why theory is useful, basically. And it's very nice to talk in the presence of the director of ITC. Don't destroy my microphone. But yeah, so the fact is that there could be actually a chance for the flare in radio if you do really actually great chance, like if you really, really look for it from the GRMHD perspective, that's kind of like theoretical laboratory for actually theory physics, basically theoretical astrophysicists and physicists in general. So what we can do actually to see is there any chance at all to get those flares in the sub-millimeter that then we can propose it to our friends in the EHD or anybody else to look for them. So the first thing that I tried to do was actually looking at the very dedicated, very long-term, 15 years of observations, mock data observation for M87, from the GRMHD simulations, from Hammer collaboration, covering black hole spin from minus 0.94 to plus 94, 5 different black hole spin for magnetically arrested distance, same, which is like a standard and normal. So these are basically a heavy magnetic field, and these are kind of like a standard and not that heavy. So what you can actually see here in the color, so there are a lot of oscillatory or variability in the light curve that you observe, but it also occurs that during 15 years of near horizon, basically, measurements or observations of the M87, there is a chance that in some points you see some actually features that are flare-like. And it's interesting because Avi already actually asked Joseph, is there any guarantee that any of them can be a flare? And that's a great point. I'm going to respond that any momentarily. But you can also see that there are some actually cases that there is no flare, in which case either for 0 spin or plus 94 that they are almost similar. So I cannot identify, this is the flux peak, but it's also equivalently similar to others and others. But there are also some circumstances in which you see more than one flare, which is actually for minus 0.94, which we see several of them. So these are very informative. When it's come down to saying whether you have thermal or not thermals, the light curve is totally different. But for mags, they're on the top of each other, which actually giving us even more confidence feeling that maybe there is something. So that's a good news. So here after, I'm going to tell you that yes, there could be a flare in M87 depending on the black hole spin. So what this actually implies is that if you do observations further and further, covering 15 years of observation, if you see them, maybe a spin of black hole is 0.5. If you never see them, maybe that's one of these cases. If you see few of them, maybe that's actually this one, and so on and so forth. But now let's just proceed and see whether the flare could be real or not. The first thing that you can actually look at them is either magnetic flux or accretion rate near to the black hole. And you can actually see that again here, there is a nice, so the orange dashed line refers to the moment that the intensity flux is actually peaky. But you see that there is basically a moment that around that magnetic flux actually is stopped in the quiescent mode. It sharply goes down up actually, and it sharply goes down, and it gets to the quiescent mode. So that's what we call a flare, and I think that hopefully you also agree with them. So we are very lucky that at least in the case that I'm going to focus in the rest of the talk on it, there is a very nice signature of the magnetic flux to goes up and goes down and gets to the quiescent mode. So let's go further down actually. The time scale for the variability, if you compare against all of the geometry simulation and compare them with the SMA data, that for instance Chen et al. With Jeff, they actually wrote it, we noticed that the time scale that we are seeing in the geometry simulations are very different than them, and that's a good signal because SMA data without the EHD actually interferometry campaign, there is no chance that you can be really probing the near horizon scale. It's just near horizon plus jet phase, and it kind of like modulates each other. So he was very interested, and maybe in the next round of ALMA proposal, we propose this so that we can buy time from the EHD observation. But let's go further. What is actually going on? Here I'm actually showing you a color plot for the intensity, and on the top of it, some streamlines for magnetic field, and you see the flux eruption basically here. I don't want you to lose, I don't want you to lose basically the moment for when the flux goes up, and then the flux basically gets, in this case it's kind of like a little bit flary, and then they get puff up, and they just basically goes up and further out, and the flux diminish, and then you see the magnetic reconnection disappear, magnetic loops they get open up, and a lot of other things. So this is really, really true and actually real that we can look for. But now we can also consider it statically. So this is before the flare, this is exactly at the time of the flare, this is exactly at the time that we see flux eruption, and afterward quiescent, in which 1 order of magnitude the flux diminishes, and afterward there is basically reaccretion and you get to the original state. So that's another indication that there is a flare going on. But now the question is that how we can potentially analyze them. So it could be very challenging, and let me actually tell you what people have been doing before I joined the EHD in this case. And they were just like, this is very famous Beta-M decomposition, that people try to decompose linear polarization in terms of different M's actually of the, of this azimuthal mode, and people normally are interested at beta equal to 2. So it's very nice, I really love them. They are my actually great colleagues. So let's see what would happen if we use beta equal to 2. And again, sorry, I'm not used to actually use it simultaneously. So we see that M equal to 2, that's exactly this point. There is no indications that you can actually see a lot of variation. So that's the first challenge for this decomposition. That is very nice, it does a lot of things, but maybe when it's come down to the dynamical imaging and variability, we have to think more about what we can do. And here is what I'm actually going even further. So if you try to use that as a method and go to different, basically, cuts that you can imagine to have, again, going back in the previous slide, you can basically go from minus O plus 1, minus O plus 2, minus O plus 4, etc., etc., and you see that the full numerics that you actually see for the phase of the EB correlation, that I will describe it in a moment, is completely misclassified by 50% if you just consider M equal to 2 cut. So we have to be very careful when we propose those metrics that may not capture all of the astrophysics near the black hole. But then for stains that are even like a weaker magnetic field is even worse actually. You see that even at the cut of M equal to 4, which is 9 modes simultaneously being considered, you are not exactly similar to, for different black hole spin, you are not exactly similar to what basically numeric is going to tell you. And that's exactly my contribution from the time that I came to the EHD collaboration in which I tried to propose a new metric. Why I did that? Well, I was cosmologist before being a black hole astrophysicist, and I was working on the CMB when we have CMB anisotropies. In fact, in a paper that we wrote with Shingon Chen, he's not here today, several years ago, we were just like saying that the EP correlation phase, okay, I'll try to wrap up very quickly, can be very informative about the anisotropies that you see in the CMB map. So since the time that I actually joined the ESU, I was asking myself what would happen if I go instead of LM mode, go to the visibility space, and ask myself, we have a lot of them, so just forget about the image space, now go to the visibility space, which is exactly where the observations goes up, and then try to ask what you actually see. And this is what you see. The EB correlation phase, it just see a lot of variations. You can define them E mode and B mode. All of us know linear polarization, and you can actually compute the correlation function and the phase of the correlation function. Now, very quickly, we did in the first round of the work, we just tried to do it for all geometry simulations, and we saw that, oh, they can be different depending on the black hole spin versus the geometry of the magnetic field. But the ending point of the talk is that I also tried to use that for the flaring magnetic field, for the flaring MAG7, and actually we see that, in the vicinity of the flare, in the phase that you're actually increasing the flux, then you sustain in the flux, then you go to the basically eruptions and then quiescent mode. There are some rotations, there are some cases that you have phase which is very small, then phase actually start rotating and then going back. So it can be really, really informative. And it's very basically non-local, non-linear. So you incorporate all the information from all the modes that is very dirty, and you cannot really understand what's going on in one correlation function, in the phase of the correlation function, in the visibility space, and you can actually see what's going on. So then you can also go to different subrings and so on. So before I end of the talk, given the success of this new correlation function, I'm not needing an official paper for the ESG in which we extend them to basically many more of the black hole spin using coral simulations, and we actually see that there is a possibility that you can see which of the basically PDFs are preferred, for different black hole spin and which of them are not preferred. So to conclude, I'm going to tell you that when the new observations come to exist, you have to have new, basically, tools. And I'm happy to tell you that EV correlation phase, maybe that's one of the things that you can actually try to do to make everyone actually happy. You can use them for basically tracing the variabilities in the vicinity of the black hole. You can trace the black hole spin or other accretions and so on and so forth. So please stay tuned for more discoveries. And since we have many more projects than the human power, if anybody is interested to join us in this effort, I would love to have them. And thank you so much. I'm sorry for being over the time. So thanks.
So Razi, one thing that can complicate matters is the Faraday rotation, right? Because you have magnetic fields and electrons, and is that Can you eliminate that?
Yeah, exactly. So yeah, that's another good question in combination of the others. So in fact, I did this in the first work. If you have the magnetically arrested disk, there is almost no internal Faraday rotation because they are very actually strong. When it's come down to the stain, as you see, they are, there are a lot of variations in between. And I mean, let me just show you, because that's such a nice actually question. So in fact, stains are really, really, really hard, So you see that even going to further and further modes. So in fact, even just changing slightly the accretion place and things like that, that's changed a lot, the EV correlation map. So, fortunately, we are hoping that MAD7 is mad, so we shouldn't be that much worried about. But in the circumstances that flare happens, and then you also change the phase of the MAD7 from mad to sane, in which the magnetic field is going to be weaker and weaker, then maybe we have to be careful. But but it's a fair point. So.
Thank you. Any questions, comments?
Or criticism,
It
you
looks
can
like everything
provide.
was clear. Let's thank all our speakers today.
I was wondering whether